Hey guys, I'm going to be proving some special limits with L'Hopital's rule, and this is a little bit more advanced, so you should already know derivatives if you want to take on this, if you want to actually understand this video, because L'Hopital's rule is basically where if you have a limit and the result is 0 over 0 or a 0 over 0 case or infinity over infinity case, you want to take the derivative of that function or that, here, let me see, or that thing within the limit and keep deriving it until it isn't a 0 over 0 or infinity over infinity type. Now, first I want to explain why 0 over 0 or infinity over infinity wouldn't work. Because usually when we have a value over the same value equals 1, but infinity over infinity is a dynamic thing and you don't know if that really is going to equal 1. And 0 over 0, it's the same thing. Would it equal 0? Would it equal... What would it equal? So we don't really like that. We want to try to put it into a value which we understand more. Okay, so now that you understand this, let's look at the first limit that we're going to prove. The limit when x approaches to 0 of sine x over x equals 1. So if we directly plug in 0 for that, it would be sine 0 over 0, which equals 0 over 0. And we have one of those 0 over 0 types. So in order to do this, what the L'Hopital's rule says is that we take the derivative. So it would be cosine x, because sine x becomes cosine x, if we derive it, and x becomes 1, because of the if x and x n minus 1, x to the power of n equals n to the n times x to the n minus 1. So since x is 1, okay, now when you plug in 0 for x, you get cosine 0 over 1. And cosine 0 equals 1, so it equals 1. First special limit proved. Check, check. Okay, so next let's prove limit of when x approaches 0, 1 minus cosine x over x equals 0. Okay, so this actually can be proved with the L'Hopital's rule and also using the other special limit that we previously learned, and I'll just show you real quick both ways. So if you want to use L'Hopital's rule, this is how it's going to go. The L'Hopital's rule is extremely simple, just looking at it right now. So derive this, it becomes 0 because constants become 0, and this the derivative of cosine x is sine x, but with the negative sign is negative sine x. So wait, cosine x prime equals negative sine x, but since there's already a negative sign here, we'll just say sine x, and x becomes 1. And once you plug in 0 for this, 0 plus sine, I should always label, I keep forgetting. Remember to label, you're going to get points marked off on tests, like me. 0 plus sine 0, which equals 0. So this entire equation equals 0. Now it's proved. Using the different, using the first special limit to prove this, I'm going to show you that. Limit x approaches 0, 1 minus cosine x over x. Okay, so let's multiply both sides by the conjugate of 1 minus cosine x. So 1 plus cosine x. Okay, now the top part becomes 1 minus cosine x. Cosine x squared. That's actually, oh my gosh, I keep reading this wrong. 1 minus cosine squared x. Because then if I say cosine x squared, they might think x is squared. But anyways, cosine 1 minus cosine x times 1 plus cosine x is 1 minus cosine squared x. And the denominator is still the same. And because sine squared x plus cosine squared x equals 1, we can say that this can be substituted with sine squared x. And because it's substituted with sine squared x, sine x times sine x over x1 plus cosine x, you can take this part and cancel it because it equals 1. And you know that because of the previous special limit we learned that sine x over x equals 1. What is left over is sine x, x approaches 0, 1 plus cosine x. The top part equals 0 once you plug in the value of 0 for x. Let's just ignore this then. This is 0, 0. And 1 plus cosine 0 equals 2. But since the numerator equals 0, the entire thing equals 0. So we proved it both ways using L'Hopital's rule and using our sine x over x special limit. Thank you for watching.